Sorry about that. I need my 10-minute break like you do. So, again, I've got enough notes to talk the whole time. I definitely want to do a couple of examples no matter what questions we have or not. To set you up for Monday, again, Monday you're going to see like, oh, well, that is a little hard. So I want to go ahead and get you kind of ready for that. And I've got 2 pages of examples that you can do. The kinds of questions that will definitely appear on the first test. I'm thinking of a van der Waals manipulation question where I don't necessarily give you the van der Waals equation, but something like it that I just made up. And a type of derivation that I'm going to introduce you to today in Monday, those will be the 2 derivation questions. So the test comes in the form of, and I'll go over this on Friday, next Friday, because you don't need to know now, but there's 4 or 5 sections on the first test. Starts out with true and false. I told you this, one statement is true, one statement is false, and you have to tell me which one's false. Then I get into a section called units, which is manipulate units, tell me what the units are, and it may be, well, this goat's a chicken. I mean, that literally might happen. It is going to happen. One time a goat was in units of Cheney's, and it was an equation for the Death Star. And then I've got homeworky problems, life, the universe and everything, and the derivation. Obviously the derivations are the hard ones, they come last. There's 2 of them, you have to do them both. The others you can pick and choose. Anyway, so that's what I'm leaning towards. So anyway, I have these practice problems. As before, I'm here to answer, mostly I'm supposed to be answering questions, it's just I find that sometimes you don't. And if you paid me here to be an hour, I will be here an hour. So I'll work that no matter what. Again, I always throw candy at people. Apparently I have a pack of Splenda. So at least it's not Steve yet, one of those. Breaking Bad. Anyway, okay. All right. Questions? Question.
Can you explain the equal partition theorem? I'm having a hard time understanding the idea of degrees of freedom.
Yeah. So. One thing is that U is exact, and that's kind of the first law of thermodynamics doing that. For U to be exact means that however U change, it doesn't matter how U changes, and that's kind of saying that energy can't be created or destroyed. That's the first law. So for U to be exact, that means the energy had to go somewhere. And that means it was never lost and therefore never destroyed. So that's the change in U is exact. If the change in U, the partial of U is exact, then U, I can certainly write equations of the change in U. I've been doing it the whole time, but that means U itself has a definition. Wait till I do entropy. That was real interesting. And there was that bit that I normally use to prove it that I was asked to cut it in 342 because it's supposed to be brought up in 346. I kind of wish that didn't happen, but not up to me. So what ends up happening again is 1/2 RT times degrees of freedom. Degrees of freedom. Okay, and the degrees of freedom are translation, rotation, and vibration. And what it comes down to is, let's see, how do I put this? I can explain this a couple different ways. For one, so this RT thing, this just says, it's a translation. So temperature is temperature, R is a translator to energy. That's its job. And it just means that if you have a certain temperature, you have a certain energy. And it doesn't matter what you are. You have this much energy by virtue of having this much temperature, whether you're a xenon atom or a protein flying through outer space. It utterly doesn't matter. Whatever their temperature is, if they have the same temperature, the xenon atom in a bottle, protein somehow shot off into outer space, whatever. If they're the same temperature, they have the exact same internal energy, same amount of energy just by virtue of being warm. But now what they do with it can matter. So translation means that you have energy, you had to have done something with it. I can't impart energy to a xenon atom and have it sit still. That's absurd. That can't happen. Now the electron, maybe the electrons do something. 346 quantum mechanics. Answer, no. It won't. So, and you have to wait till 346. So if I'm going to, put xenon in a little skillet, it's got to do something, and it can translate. So it will do so. Now it can go up, down, left, right, forward, or backward. There's three ways to translate three-dimensional universe. And I told you that little Stephen Hawking bit that came out on, it was on CNN, that where we all exist as the skin of a black hole in a four-dimensional universe. Like, that's kind of cool, but anyway, I don't know anything. But, so that's just what you're going to do with it, do with that energy. And that's also why that affects heat capacity. Because this is what you did with the energy, and it isn't necessarily going into feeling warm. Okay, rotation is 2 for linear, or 3 nonlinear. Almost everything is nonlinear, right? Except that gases generally come in the form of N2O2, neon, argon, helium, H2. So a lot of gases are actually pretty small because of U2. Or 0. AR, HE, NE, XE, okay, that's obvious. And remember, we talked about how you can't roll an atom. And remember, this is why the linear molecules don't rotate this way. It's the same thing as rolling an atom. We talked about that last week. This is not happening. Doesn't make sense. Okay, again, this is just something you can do with that energy. Now, part of the equal partition theorem, part of its purpose is, it says, okay, I've given you 200 joules of energy because you are this warm. So that's about room temperature. If you can translate, you can. If you can rotate, you can. And nature gives each one of those degrees of freedom just as much energy as the other degrees of freedom if it can. Right, so just because I'm on rotation, I can accept your energy. Nature says, well then here's your equal share. Rotation, translation, you have your equal share. I've split it in two in this case because I have 3 rotations and 3 translations. Methane will take half the energy and rotate with it, and the other half the energy and move with it. And we can measure that stuff, it's true. Vibration, now notice this. This is kind of actually involves a little information theory. That's a branch of mathematics. It turns out that motion, the number of ways to move, however you move, depends on the number of atoms. So this is the number, that's the number of atoms, and that's the total ways you can move. It makes sense, right? For not, this does not apply. Sorry, this doesn't apply to these guys. All right, now it turns out that, sorry, my bad. 3 dimensions, my bad. I'm an idiot. Sorry, this does apply to these. Brain just fell on my head for a second. No, this doesn't apply to these guys, does it? Sorry, my brain just isn't working right now. Yeah, this doesn't apply to these guys. So again, the number of ways a thing can move is the number of atoms times the fact that we live in 3 dimensions. But I'm talking about one particular form of motion. So I have to subtract out the other motions that aren't in this category. If I'm linear, 3 plus 2 is 5. All right, these are not vibrations, therefore I take out the total ways of moving and subtract the things out that don't fit in the category. 3n minus 6 or nonlinear. Right, and that's where that comes from. I think you were just fed that as freshmen. You were just told this. I doubt they explained why. I don't know. Maybe they did. Who knows? If not, so now you know why. So, there you go. I don't know I can do much better than this, and this is also why, and again, you should make this an instinct at constant T, the change in U is 0, and the change in enthalpy is 0. Half your questions will be at constant temperature. Ammo, that's 2 points, or 4 points, depending on the grading scheme anyway. And you got your candy. It's poison. Anyway, other questions? Question?
Why is the vibrational degrees of freedom negligible?
Ready for this? Close. Anyway, sorry, what was the question?
Why are the vibrational degrees of freedom, like when you add like U equals U naught plus whatever? Why do we ignore the vibrational?
Why do we ignore them? Right, so remember, these have to act as heat sinks. And again, so let's say that by magic, I can hold a molecule stationary. It'll be a molecule, this will be M2. By magic, I hold the molecule stationary, and I feed it, and it's on a skillet. I'm feeding it energy. Now here's the problem. I'm going to warm it, and I'm using a skillet, which means I'm operating at roughly terrestrial temperatures. Yes, it feels hot, but on the Kelvin scale, even a hot iron isn't really that hot. 350, 250, whatever. That's divided by hundreds by 350 is not that big a number, right? So here's the problem. So if I could do that, if I could pin nitrogen such that it can't translate or rotate, and I feed it energy, and it can only vibrate, well, the laws of physics just broke down. Because I will have fed it energy, and it won't have been able to do anything with it. So sorry. I know and I have a mole of them, so I'm using R as opposed to the Boltzmann constant. Details, don't worry about it. So I have a mole of xenon. I'm magically not letting them translate. I'm magically not letting them rotate, and I'm feeding them energy, and they're taking it. Well, that can't happen. That's in a different universe, and it certainly isn't. Who cares? It's not in this one. Because the amount of energy that I can impart with a little skillet and a little flame, I just moved in a building with gas, so now everything's flame. It's not enough to absorb. It's not the energy of a quantum step. It can't vibrate faster. Now again, remember I just said, you give it energy, it must do something with it. And translation is always easy because that's very little energy. The translational quantum levels are so close together, I would just make this whole thing just black essentially. So it's easy for it to translate with its energy, but again, by magic, I've stopped it. It's easy to rotate with extra energy, but by magic, I stopped it. But again, you know what the molecule would do? Even if I put it on a skillet and I magically did that, it wouldn't accept any energy because it has no way to use it. Again, because the amount of energy I have is not enough to overcome this quantum step. It is not a legitimate energy sink. So remember, also I said, things vibrate at this level, like this, and if suddenly you did get it hot enough, which is really, I'm serious, inside of a rocket engine, it takes incredible amounts of temperature to get it to get RT this big. That's a gigantic amount of temperature. What it would do is, all of a sudden, that vibration did become a legitimate heat sink, somewhere the energy to go. It instantly does this. Instantly. Time equals 0 seconds to do this. And I cool it back down, then it must instantly go back to that lower vibrational state. So again, for this to absorb energy from my skillet has to be glowing, melting, rocket hot, and it's not. I'm not going to, this isn't rocket class. I bet NASA does have to worry about that kind of stuff, but we don't. So effectively, we say that they're frozen out. That's the word for it, frozen out. Because we are freezing. If I was a vibration and I touched me, I would be freezing cold. That's how they would perceive me. So just another way to think about it. Is that okay? Best I can do. Any other questions? Been heard?
I'm a little confused by the concept of external pressure, like in the context of calculating irreversible work.
Well, now, again, let's do the magic piston thing. And the magic piston's not, so I'm at, we're 900 feet altitude, I believe, if I'm not mistaken. Funny enough, that's actually the same height as Niagara Falls. If Niagara Falls actually it's moving back closer and closer towards us. If it ever hits Lake Erie, all the Great Lakes drain. It's a little factoid. So anyway, So we're a little bit above sea level. So we're at slightly less than an atmosphere. Let's just say it's an atmosphere. Now the piston is where the piston's at. We'll make it slide without friction. The piston's interior is at 1 atmosphere. If it wasn't, the piston would be moving. It's not. So it's at 1 atmosphere, I'm at 1 atmosphere. And the idea of irreversible is the thing has a plunger, right? So again, I think my drawing is okay. I actually did draw all those stressed out animals, by the way. So here's the plunger. So that's the piston, I guess this is the plunger. And this is my hand pushing on it. So I can push on it. Now I can either instantly add 2 atmospheres of pressure. Now, not really, but I can add those 2 atmospheres of pressure such that this thing will have movement, it'll be just a really tiny amount. So for the most part, it's going to compress at a constant 2 atmospheres of pressure because that's what I did. And that's irreversible. Now again, the reversible is just very, very slow. My additional pressure is delta P. So remember, it is always, P without a thing is always interior. Okay, so I'm adding a little bit of pressure, but it's a partial, right? Meaning it has infinitesimally low value. And so that way, the exterior pressure is always equal to the interior pressure because this is effectively 0. And then it's reversible. And the way to understand why that's maximum negative work are those graphs, and that's great for you graphical people, but it's absolutely true. I mean, as much as a graph is not an equation, it's absolutely correct. It is the rate of negative work, and you did that on your last homework. And also notice that reversible is infinitely slow. I mean, how fast can I change? Not at all. Well, it's going to take a very long time. So, effectively, people have tried to build nearly reversible engines. It's called a Stirling engine. You can Google it. You can even buy these things. They're just like the most efficient engines that anyone's ever made. And again, nothing is ever truly reversible because a reversible engine would take forever to move. But you can get kind of close, and that's the idea, that it's kind of a slow-moving thing. Anyway, are we okay? I mean, it's just, I'm pushing or I'm pulling. That's all it comes down to. It's just a matter of how I chose to do so. And of course, I push, traction, and my pull, expansion. Just that easy. Questions?
Real quick, just to go back to that. You said that N2 had a U of 5/2 RT.
Mm-hmm.
That would be the translation 3 plus the rotation 2?
2 because it's linear.
Right, okay.
Exactly. Right, can't do that. Other questions? Right there.
So based on what you said, you have a question about acid count? Is it, because it's not linear, so I mean, you can have more rotations than 3 for non-linear molecules.
Right, 3 is it. 3 dimensions. You're done with rotations.
So I just don't see how you can make sure if you get it is because of the molecular binding.
You saw that drawing, right?
Yeah.
Look,
Okay.
I'm with my hair, I'll let you know. I mean, do you see it moving another way?
Yeah, I can see it moving there.
Right. Now the trick is that those internal types of twisting. Here we go. Oh God, I'll leave right there. God, be careful. Oh wow, first time. Okay, so those rules are a little bit nebulous about vibrations and rotations. Take I2 minus. I2 minus vibrational frequency is actually extremely low, meaning that its quantum levels are, because of its very low vibrational frequency, it's barely above RT, so it doesn't take much heat for I2 minus to start actually using energy to vibrate. It doesn't take much heat at all, but I2 minus is kind of special. It's like the weakest bond in nature. And we can make I2 minus in the gas phase and look at its spectrum, and that's how we know these things. So rules are meant to be broken, essentially. And let me try to think of another way to explain it. So as much as I'm telling you, no, you can't include vibration, it's because most things practically have very, very strong spring constants. Bonds are like springs, right? They have very strong spring constants. strong spring constants mean that these levels are very big compared to RT. So that's why they're frozen out. But there are exceptions, and I2 minus is one of them. I didn't bring it up because it's kind of rare. But now think about this thing, like ethane, the trans, gauche, eclipsed, and all that. You know, this, that is doing this. You know, do those Fisher projections. How much energy does that take? Because that would be another degree of freedom. Now, reality is, it's a decent amount of energy. It doesn't seem like much, but it actually is. So you tend not to count that. But now imagine like I2 minus, as you can imagine, that certainly sounds like a pretty barely held together molecule, and it is. And therefore, its heat capacity is actually kind of high, much higher than 5 halves RT, right? It's I2 minus should be 5 halves. It's much higher because the vibrations actually are kicking in, even close to room temperature. So this guy, this part, right? I did acetone, right, this year? Yeah, I did acetone. This that I drew, maybe that doesn't take a lot of energy, right? And normally it's a decent amount, but if it's not, if it's like this, then maybe it is kicking it a little bit and driving heat capacity a little higher. That's the idea. All right, and here's another example. I always do this for teaching for biochemists, but I mean we shouldn't necessarily just ignore a biochem in this class. That would kind of be wrong. All right, so proteins can form helices, alpha helices, and they form beta sheets. And then there's another form called a polyprotein structure, whatever, here. Anyway, now imagine, this looks like a giant spring. Imagine we could shrink ourselves down and hold on to an alpha helix and play it like an accordion. Would that take a lot of energy? Does that sound like stretching a CH bond? That's a pretty strong bond, by the way. I'm pretty sure I could pull on this thing a little bit. I bet it wouldn't take much energy at all, meaning it's a degree of freedom. And it can absorb energy, and notice it's not really a translation or rotation. I guess it's a vibration. Actually, we have words for those like, it's a vibration, but it certainly is low energy. Sometimes we call that a libration, and those would actually drive up your heat capacity. So I'm actually going to talk about that next Friday. This concept of degrees of freedom are actually really kind of difficult to describe because this alpha helix being used like a spring, that's a degree of freedom, right? And that's also why when I do this stuff, I tend to stick with nitrogen and methane and xenon because they're kind of perfect examples. They're really dead on in terms of their heat capacities. But I do want you to know that it's not a perfect rule. And the reason is because what we call a degree of freedom is actually really hard for us humans to understand. I certainly understand N2 vibrating. N2 vibrating, that's very simple. I can imagine it in my head. I can tell you that it takes a lot of energy to jump in quantum levels. I can tell you at room temperature, it just doesn't matter. But when I get a protein, which is a very hard thing to understand, in terms of all its atoms, its degrees of freedom, this accordion-like motion, hey, maybe I can bend it. Can I just grab the two ends and bend it? I bet I could, and I bet it wouldn't take much energy. Is that a degree of freedom? Sure it is. But where do I bend it? Does it matter if I bend it over here? Is that a different degree of freedom? Well, now I don't know. I'm getting confused. So this is correct. It's just that what we call a degree of freedom really can get complicated, really freaking quick once you start talking about bigger things. So anyway, that's the best I can tell you because it confuses me too. And I can give you another example. Well, I'll just go ahead and do it. We'll talk more about this on Friday. All right, argon. I asked, can argon vibrate? Of course not. It depends. It kind of can. If you lower the temperature to right before liquefaction and raise the pressure, argon, because of that dispersive interaction, the induced dipole, they will transiently pair up and vibrate. And we actually had a speaker from the University of North Carolina, he's like super famous, because he was the first guy to see that. He actually got the vibrational spectra of argon. It's a trick question that we got sometimes in our PhD exams. Hey, what's the vibrational spectra? What's the infrared spectra of argon look like? It'd be a question that sometimes we get asked. And the answer is there is none, because it doesn't. Infrared radiation is vibrational radiation, and argon doesn't vibrate. The reality is, if you get the conditions just right, they'll pair up briefly, and they will vibrate, and you can measure an infrared spectrum. Just got to get the conditions just right. Again, I said that argon could vibrate. Well, it can. Now here's another thing. It doesn't last long. These encounter complexes, they'll do it. They come together, they'll vibrate for a nanosecond, and then they fly off. All right, it's a degree of freedom, but it doesn't live very long. So is it 1 degree of freedom? Doesn't sound like it. It need to live forever, and it doesn't. These things get together for a nanosecond, they fly off. Is that half a degree of freedom? I don't know. I have no idea. Nature knows, but I'm just not that smart. So anyway, I know it just threw a hell of a layer of complication on there, but that's the best I can do to explain it. And that's why I'm going to stick with easy examples. But again, I want you to know there are deviations. You can see them in the heat capacity table yourself. I'm just explaining why. Although, unfortunately, the answer is quite complicated. That's best I can do. Other questions? Question. You ready? All right, awesome.
You wrote an equation with H and U and PV, and made a substitution, and then said it's isothermal, so the DT goes to 0, and that DH equal to DU, but you didn't say that. You said DU and DH are equal to 0. Why equal to 0, not equal to each other?
Well, that is the same thing. If they're both 0. Right, well here, let me just do it again. So, equal partition theorem, again, that you get a star, constant T, we're obviously already breaking out a constant T as we speak. But a constant T, equal partition theorem, which you remember that's going to start by it. That means that if temperature doesn't change, then the internal energy doesn't change because it's purely, the only thing that changes is temperature. So that's automatic. And again, I have to ask you to simply accept the equal partition theorem. I hate that, but that's one piece I had to do it. Let me just do the derivation again. And yes, they are equal. Change in U plus the change in PV. And remember that you've got to be able to do this. Remember, because we're going to have a lot of changes of this kind of that, and you have to treat it like this. Okay, now that's true, but I'm telling you that is a very difficult thing to work with, especially if you have a situation where pressure and volume are changing. It's like, well, if they're both changing, then what pressure do I use? And volume is changing too, so what volume do I use here? It's kind of confusing. Here's a better way to do it, is just substitute an RT. Because I'm only doing gases anyway. Later we'll do other stuff. Change in T, and T isn't changing, just it's like equal partition theorem all over again. There you go. Yeah. So imagine if temperature is changing, because we are getting to that, you do have that on the homework, this gives you a route to solve it. You would take U, whatever, and so when temperature is changing, U would be a number, and you're going to do that on the problem set. And you can figure it out by working heat. Heat, I give you heat. And then take that U and then add this to it when the temperature actually does change, because you do have some of that on your homework. Relatively straightforward. So, our office hours if you have trouble, right? Okay, another question?
Yes. On question 2, problem set 3, you talk about dQ and dW, and I thought you said, when we're saying that, we're talking about an infinitesimal, essentially 0. But then, at the bottom there, you're talking about hints here, dQ equal to 2.33 negajoule.
My symbology is very bad. dQ would automatically be 0 joules. Joules. I'm just very bad about terminology. I need to say this. Right, I'm just using the symbols wrong. I'm just very bad about that. So I should have put a delta. And so it's the integral of heat. But if we're at constant, I think that's a constant temperature question. That would be minus the change in work. And this would be minus P E X T dV in reverse. And of course it is minus nRT ln VF over VI if it's reversible. No, plus, sorry, plus, sorry, my bad. I gave the formula for work, but I forgot that heat is minus work. And again, if you get the symbology right, I'm trying, I just really screw it up a lot. It's too much to get in my head. When do we get to some of the delta G stuff, where delta G's are labeled by 3 or 4 different set of symbols to represent how delta G is the conditions? It's pretty, especially when you do electrochem, and you've got symbols out the wazoo. And you don't really, they're not essential to answer any of the questions at all, but I try to get it right, but I screw it up a lot. Yeah? Are you okay? Anybody else? Okay, how about, okay, my example problems, let's do that. I really do want to do 2 or 3 of them. All right, in terms of the quantum thing, I clearly don't have time, that's fine. Tell you what, later in the class, which is better, later in the class, I'll do some quantum mechanical math because I can tell you up until maybe halfway through the class, we're going to be in some starting Monday is when we're going to start to get into more of the difficult stuff. Towards the end of class, I will sometimes cancel the second hour. I will do that sometimes if there's just really nothing to talk about, especially towards the end of the semester. You guys will be feeling kind of nutso on me. Summertime, you want to get out of here, and I get that, me too, in all honesty. So I'm going to war. I'm going to the Naval Research Lab. As soon as class is over in the summer, I got invited to talk. That would be kind of cool. I think I have to get security clearance. I hope they don't find out about the incident. Never mind. Literally, a friend of mine was telling me about how this guy's ex-roommate was getting top security clearance, and they will go talk to your friends and knock on their door. So the guy told us, like, hey, buddy, just so you know, just answer the guy's questions honestly, but I'm applying for top secret security. And the guy didn't, here's the thing, they don't tell you when they show up. So the guy, Sunday morning, where can I? It's fried chicken. God, I'm in so much trouble. So the guy gets up, there's a knock on the door, and there's this military guy who sits down and asks him all kinds of questions as he's sitting in a sea of empty beer cans. And the guy got, look, he's not his friend. And his friend got the security clearance. So anyway, I thought that was kind of, it happened to me once when these Jehovah's Witnesses knocked on the door, and me and my 3 roommates are shirtless, like playing guitar, and we cleaned up all the beer cans. We're here to talk to you about, we looked at it like, lady, why don't you just look at us? This isn't going to go well. Okay, practice with partials. I'll just show you 2 examples and we'll break. I only got 2 examples. Engineers, you're familiar with this. This is called the isothermal compressibility. Don't worry about that. I won't. This is definitely one of those things I don't want you to try to memorize. It's going to come up once or twice. And this is, I have a material, it's something you use more for solids. I'm going to put the material under some pressure and its volume is going to change. All right, if pressure goes up, the volume goes down. All right, so is this positive or negative? Negative over positive is? Right, so K's are automatically negative. Now, back in the day when we started figuring this stuff out, people didn't like to publish tables full of negative numbers. We just don't like negative numbers in general. So we multiplied it by -1. So it became positive. It was just how we decided to define it. Now, here's another thing. You want this to be general. Now, if I put a cup of water and I push on it a little bit, this volume's going to change a little bit. Now, if I, let's say it changes by 1%, which is actually unrealistically high. Now, I do it to the ocean. 1% of the ocean's volume, is that greater than 1% of a cup's volume? Yes, of course it is. So they did this. All right, this way it became not intrinsic. What's the word? God, I just put it on the last homework. It's intensive. It becomes intensive. Right. So I can just give you this number for water, and then question.
Yeah. Why is it? Does it not change much the volume because of that number?
What it does for the case of water?
Yeah.
It's just because it's condensed. There's not much room. The waters are so close together. There's not a lot of spare room to squeeze it into. So solids and liquids, you can't really compress them very much. You can, and you can measure it. small, much less than a percent. If you use a huge pressure on something, barely changes at all. But it does, and it's measurable because we've got good machines. Now, let's do this for a gas though, that's easy. Okay, so I'd ask you this, I say, what's this for a perfect gas? Now again, I know that some of you are thinking, child's play, wait till you're on the test. All right, so I said it's a perfect gas, nRT over P. Therefore, PV, PP, and a constant T. Now this is again, is a time that what's held constant really doesn't matter. Doesn't matter at all, that can be minus nRT over P squared. Over P squared, right? Now, just for the heck of it, I recognize that nRT over P by itself is volume. So this is minus volume over pressure. Okay, so now let's do this guy. Minus 1 over V, minus V over P, 1 over V. So, you're on the test. This is the isothermal compressibility. Show me that it's equal to 1 over pressure. Oh, I'm bloody likely to do that. This would be in the easy section. We have true and false first, then next is the easiest section. This is an easy type of section question. Maybe, if I'm being generous, it's in the next section. It's not going to be a derivation section. Not even close. It's too easy. All right, so anyway, and notice I also gave you the answer. Again, hopefully you're really getting used to that. This last test, I went kind of nuts on it. Also, did the units work? Right? Does it make sense? Right, because I'm saying, here's the question on the test. This is equal to that. Does that make sense in terms of units? What's your answer? Well, yes, because dV has units of volume. That's the actual question. Recognizing that partials still have units. This has units of liters, this has units of pascals, but I have liters over pascals, which is 1 over pascals. Totally makes sense. That's the answer. Dan Lowe, that would be a 5-point question. So look for that kind of stuff. All right, child's play. Child's play. Let's do a harder one. Here's one more. Now this is going to be like what we do on Monday. This is kind of neat. It's actually going to be part of the derivation. I'll show it to you now. I don't want to waste your time showing you the same thing twice, but sometimes it's not such a bad idea. Like we were talking to the faculty meeting, we're like, wait, we can't repeat things twice. And we're like, no, sometimes it's good for them to see it twice because they probably forgot. Okay, so I've done this. I did this today. There wasn't much of a proof. I'm just saying it is. Okay, now what about this? Change in temperature at constant pressure. Right? It's different. It's a different thing. I'm not holding pressure. I'm not holding volume constant. I'm holding pressure. Now there are things that are path dependent, so this could change. I want to give you a hint. U is not path dependent, so is it going to change? Now, okay. Now this is exactly what you've got to get used to. This is a very simple version of what we're going to be doing, which is going to be kind of hard. The first thing to do is expand the change in U and use this proper change in a function form, multivariable calculus. Now I'm thinking, I'm going to talk about the change in U with respect to something and the change in that something at constant something else. But what do I pick? I don't have to pick one. Right? So I'm looking at this and I'm thinking, all right, I've got to do temperature. I'm going to have to expand this about temperature no matter what. Absolutely. I absolutely have to do that. Because this is central to the question. Now, it seems like I might want to hold pressure constant and do this. Now, what I'm doing right now is I'm simply saying, what is this? Now, you have to begin here. You got to begin somewhere. And then do some derivations. Now that I've done this, I decided I'm going to look at temperature and pressure. I held pressure constant here. That means I have to let it change here. As soon as I decided this, then it's automatically implied that. That means temperature is held constant. So there aren't many rules to this, but again, I know that I'm looking at changes in temperature, so it makes sense to expand U about temperature. And I've decided that I'm doing this at constant pressure, so I think my other guy ought to be pressure. Now the trick to this is I need to get this. So I'm going to divide by the change in T. And this guy doesn't get affected. This guy doesn't get affected. And again, we're done with, sorry about this, we're done with this. Okay, and I will, you see, I've drawn this out. I've drawn this out. Okay, I have a slight problem. Okay, what's the change in P with the change in T when P doesn't change? 0. This gets wiped out. Okay, this is 1. So I've got the change in U with respect to T at constant P is equal to the change in U with respect to T at constant P. While true, that blows. That doesn't help. Lesson. I picked the wrong variable. Now again, I got to work with this. This is just too central. But nothing says that while it seems like I want to expand the T and P because that's what I have in here, not necessarily so. So trivial answer, no points. Well, I give you half credit. Let's do this. If I can't expand about T, I'm going to do it about B instead. It's the only other logical choice. Now, by the way, I'm not going to throw you to the wolves. I'll give you a very good idea how to start, because I don't think you could write so many different forms of this and never get it right. You really have to do this the right way. I've done this so many times, my instincts tell me what to do, but you haven't. I'm aware of that. Like I say, I'm conscientious of that. So I've decided to expand U about T and V. Now I'm going to divide by P and hold P constant. Hold P constant. Okay, and this of course is what I'm asking. And now I have an answer. Let's see. This guy turns to 1. Du, dt, constant V. Now here's the damnedest thing. Okay, I can do the change in volume with respect to temperature, constant pressure. We'll do perfect gases, and that will be NR over P, by the way. Don't worry about it, because it's multiplied by something else that is a problem. How does U change at constant T? The thing you need to spit out instantly. 0. 0. This, what's du dt at constant V? Of course it is. There you go. So, anyway, yeah. So what it means is that the change in U is path independent. It always was. It has to be. No matter what you try to figure out, when you try to screw around with U and change paths, change processes, it doesn't matter. For the same change in temperature, you will find the same result. It doesn't matter how you did it. Right? So there you go. There's that path independence kicking in again. Okay, we're short on time. I got one more good one I want to show you. Before we do, so what we're going to do first thing Monday is I'm going to calculate, I'm going to derive the Cp minus Cv, and that's going to be dH dt minus du dt. But let's do this one. dH dt at constant pressure is Cp, but at constant volume it is what? There you go. Now, I already just blabbered on about how your instincts may be to expand H about T and V, and T is correct, but V will lead to the null result. I'm just going to tell you that. So let's expand it against P. Again, I know that temperature has to be part of the mix, and I can expand it about P. Now, as soon as I hold P constant, I'm obliged to write the next thing. I have to let P change while I hold temperature constant. Okay, I have to do that. Now the question is to do the change in temperature. So, sorry that it's blending together. Sorry about that. Not giving myself enough space. Change in temperature. And again, remember, I'm allowed to make whatever constant I want. It's just that I can't touch this. It's done. I can't touch that. Whole volume constant. Okay, now, T over T doesn't matter. 1 dP dt, will that be NR over V? But, change in H at constant T? 0. This goes to 0. And I got dH dt at constant P, which is Cp. So even though CP is a number that is only applicable at constant pressure, it actually doesn't matter because of H's path independence. If I'm changing temperature, if I have to change in H, I still use CP. And let me show you another manipulation I can do. I've got 1 more minute. All right, so I have a constant volume question. And we're not going to, let's make it a heat question, like on your homework. Now, if it was the temperature's going to change, and you're going to figure it out with heat is equal to, let's say, constant volume, heat capacity times the change in temperature. I gave you the heat, I gave you the heat capacity, constant volume, you now have the temperature. The temperature has changed. We're at constant volume, so that would be the change in U. So U now has changed because temperature changed. So anyway, now I've asked for the change in H, and I did do that on the homework. Now, you might be tempted to do the same number, but you don't. What you do is exactly this, and then you integrate. And what you get is, again, both heat capacity a constant as a function of temperature. Sorry, dT. And now that I've shown you this, that'd be CV plus R, NR, delta T. So anyway, now you can get changes in H. And yeah, I guess that's, I had one other, but it's fast and over. I want to do this one another time. So anyway, all right, so again, just I hope you see that these are the kinds of calculations you're going to be doing. These are much easier than the ones I'm going to give you, but I will be very friendly and give you starting points, because I know what to do because I've done this 10 times now that you don't. So when you have these questions, I will help you with starting points, and you do what I do, and you're fine. I'll see you Monday.